Martin.
Okay, so I'm starting the live event now.
Okay.
Just give it a minute, and we're live.
Okay. So I see Martin. And
okay, but you're talking to the students, so that's okay.
I'm talking to the students now. Are they able to see my picture?
Yep, they can see your picture.
I see. And I see a big picture of Martin. So filling up my screen. Okay, so hello, everybody. Presumably everyone can now hear and see me, correct? So I've got some questions. Shall I just start? Does that sound right, Martin?
Yeah, just jump right in, Steve, please.
Okay, well, the first question is from Farouk, and it says, in the reading materials 2013 review article, the wavelength in the reduced scattering coefficient equation was normalized by a wavelength reference of 500 nanometers, which falls between cyan and green. I'm assuming this has to do with the common properties of the spectra of the previously mentioned 7 groups of tissues. Could you elaborate? Okay, so I think the latter part of that is going off on the wrong track. The key story here is when you say that scattering is proportional to a wavelength to the minus some power, you can't take units to some power, so you have to normalize. So you can normalize the wavelength by 1 nanometer or whatever you like. I choose 500 nanometers just because it's sort of in the middle of our spectrum that we usually use. And hence, I get a number that's sort of realistic. Like I might get 10 or 20 inverse centimeters when I do it that way. So I'd say lambda over 500 nanometers, in close parentheses, raised to the minus 4th power, or to the minus 1 power, or to the minus b power. And then I get a number that's kind of realistic, like 10 inverse centimeters. Whereas if you put 1 nanometer, you end up with something like 10 to the 4th for the multiplier. So I've always preferred to reference it. So it's merely a reference. You can choose different numbers, it doesn't matter. But since I do it all the time with 500 nanometers, it allows me to quickly compare data from different, experiments. Let's see, a second question from Hampus. Hampus from Lund University. You mentioned in the reading materials the narrow angle scattering is dominated by cell level structures, and wide angle scattering is due to small structures. Is this something that is or could be utilized to isolate the different parts of the tissue when one or the other is of interest? All right, this is an excellent question, Hampus. So the work has shown that if you look at the angular scattering pattern and you consider the cell as a whole or the nucleus, you'll end up with this very narrow scattering, very forward directed scattering. But if you consider the very small scale, submicron and nanoscale structure within the cell, which would be the cytoskeleton, the lipid-water interfaces of membranes, such as the membranes within a mitochondria. All of this leads to more Rayleigh scattering, Rayleigh limit of knee scattering, Rayleigh scattering, which is very broad or almost isotropic. And therefore, the broad scattering is that small scale. Now, your question is, could you use these to isolate? Well, the answer is yes, because if you pass light through a cell, but you do some interferometry where you send the light, a reference, around and then remix with the transmitted light, and then go into the Fourier domain, the Fourier plane, and acquire with a camera, you'll end up with a digital picture, which is a real number distribution. You take the Fourier transform of that, and you'll end up with imaginary numbers, and now you have a digital hologram. Now you can recreate the digital hologram. With the digital hologram, you can now do another Fourier transform, get back to a real picture, but you're able to scale, only use the central 10 degrees of the hologram to create the picture based on nuclei, and you can use the outer angles, the broader angles, to create a picture, and that'll give you a picture based on everything else. So the answer to your question is yes. Using holographic techniques, you could actually create two pictures, one due to 10 degree or less scattering and one due to broader angle scattering. Okay, let's see. Annie says, could you please explain how wavelength changes in spatial resolution, how wavelength changes the spatial resolution when imaging? Not just the mathematical relationship, but conceptually. What's going on in the interaction between the light and the object being observed that changes resolution? Oh gosh, that question is a little, it takes some dissecting to make it clear exactly what you're asking, because you're asking a good question, just it's very broad, and how to answer it. Probably more than I could quickly answer now. As you go to shorter wavelengths, yes, you get better spatial resolution, but I can't quickly say anything more than the standard mathematical relationship. So I'm going to have to pass on this question. I don't think I can give you a clear answer quickly. Meng Li asks a question. If you add so much absorber, would the absorber start to behave like scatter at some point as the absorber has finite size? Does Monte Carlo take this into consideration? Well, when you add an absorber, presumably we're talking about a molecule that absorbs. And if you add more of it, you've simply increased the concentration, the number density of absorbers, but the absorbers are still small molecules. So just because you add more absorber, it doesn't start scattering, no. However, just to be clear, you get refraction based on the refractive index, and I believe that occurs with both the real and imaginary number. So it is possible that high absorption can cause scatter. Whether it can cause it as an angle deflection, I'm not quite sure, but definitely it can cause it from the point of view of specular reflectance off a surface. And I can say this because there's been work published on the reflectance of far infrared light from teeth. And because the absorption at certain wavelengths is very high in teeth, the reflectance from the teeth actually goes up due to the absorption, due to the imaginary part of the refractive index. And therefore, I can say that yes, absorption can cause a change in reflectance, but how it might change scattering, I'm doubt. And basically, I would answer no to your question. Okay, David McMahon says, in your slide about the angular dependence of scattering, it appears that as d, the particle diameter, gets larger, G1 doesn't tend to 1, but to 0.85. Is there a reason for this? Let's see. I imagine it's because there's still a finite size involved. And so there's still a little bit of slight angular dependence. A 0.85 is somewhere in the ballpark of like a 30 degree deflection angle, 27, 30 degree deflection angle. So it's still very forward directed. Probably only if you had well, yeah, to get to 1 would require a very broad situation, almost like a linear array of, almost like a planar change in refractive index. So I don't have a quick answer for that. let's see, the next question is from Julia Mathes, and it says, which are the criteria to choose the me-scattering model rather than the Haney-Greenstein? Also, you said the me-scattering is still under research. What is the possible developments and expected results? Okay, the first part of that, the criteria for choosing me-scattering versus Haney-Greenstein. Well, the me-scattering model is used because it's well-defined. So you've got these little spheres. You can calculate how things would work with little spheres, as long as the little spheres are separated and acting independently. But of course, tissue is everything's all glommed together. It's very complex. Things are aggregated. So the me theory fails to act the way you wish when you start having things aggregate into clumps. Still sub, nanometer scale or sub-micron clumps, but nonetheless clumpiness. So when you start to actually do experiments on scattering or to describe scattering experimental data with an equation, you end up using other types of models. The Haney-Greenstein model is well known, widely circulated, and that's what you refer to here. But there's actually a variety of descriptions of scattering functions. And for example, the Gegenbauer scattering function is a more broad statement for which Haney-Greenstein is just a special case, So description of scattering using Haney-Greenstein or other descriptions are descriptions that try to describe the complex, the behavior of the complex tissue, whereas me-scattering is a very particular model which has both strengths and limits. The strengths, it's well defined. The limits, when things start getting close together, it falls apart. And as far as the possible developments, well, I had been working on the relationship between a size distribution, size to the cap minus capital B power, that fractal distribution of sizes, which can vary in a tissue. You have more mitochondria, less mitochondria, more collagen, less collagen, big nucleus, small nucleus, all that adds up to a distribution of sizes. And then that capital B is related to the lambda to the minus small b wavelength dependence of the reduced scattering coefficient. And I show a relationship there. And it's a very nice, interesting sigmoidal curve, which indicates how macroscopic measurements of the wavelength dependence of the reduced scattering, which gives you that minus small b behavior, can actually map nearly linearly, it looks like, to the capital B for the size distribution. So you learn about nanoscale structure distribution from a macroscopic measurement of scattering versus wavelength. That's neat. But there's still caveats in there. When things start to get clumpy, then what's that do to the math? And that is where it's still under research, trying to understand that relationship. Okay, Truly Chatterjee asks, you discuss modeling the scattering of light from tissues. Can we use similar models for a monolayer of cells? What would we assume differently? Okay, very good question, because a lot of what I was talking about was from a semi-infinite tissue, where it's a volume of tissue and the photons can move around in there and eventually come out. When you talk about a single monolayer of cells, there's no room for diffusion theory to set up, for example. So then we have to rely on Monte Carlo. Now with Monte Carlo, you're specifying the parameters of absorption, scattering, coefficient, the anisotropy of scattering, G1, and that's sufficient that with Monte Carlo, you can deliver a collimated light or a focused light, and the behavior as it moves through the tissue will be well defined. So if you have monolayer cells use Monte Carlo simulations. You cannot use diffusion theory. Okay. Guangjing Jiang asks, I think that Monte Carlo simulations didn't consider the boundary condition because Monte Carlo simulation is a stochastic model. Okay. Well, that statement is not necessarily true. You can include the boundary conditions in Monte Carlo simulations. In fact, we do. And MCML, for example, MCML.C, the well-known multi-layer Monte Carlo, allows you to actually change the refractive index of different planar layers in the model. So, so you actually can include boundary conditions in Monte Carlo, and it does just fine. So let's see, Jeremy Gilbert asks, can diffuse light transport theory be used to describe the propagation of monochromatic light and interference effects? Well, Jeremy, the answer, I believe, is yes, but I've found different people having good success and bad success with that. I've tried it myself and at some point had to set it aside because I didn't get to a satisfactory end. The reason is that the resolution you're talking about, spatial resolution you're talking about for interference is on the wavelength scale, and yet you're usually delivering light in a model on a little bit more macroscopic scale, like a millimeter or so. And so when you try and do that modeling, you're pushing the limits of the ability of the Monte Carlo to actually track the scale of behavior on the very small scale. I think it can be done, though. Everything about it suggests it could be done because you can track the phase. You know, in Monte Carlo, we're sending in packets of photons, or a photon with a weight, if you will. That means it can actually have a phase which will change according to its path length. So if a photon goes in and scatters its way to a point, you can actually say what its phase would be. And you can record that when you record the existence of a photon at some point. If you run millions of photons and you track the phasor, you know, of photons at that point of interest, you'll now have a population of photons with different phases. You can then do you know, what's the term? An addition of imaginary numbers. You're able to add up the phases of all of the photons at that one point, and you'll end up with a net phase. So yes, it's absolutely possible, I believe, to do Monte Carlo. It's just that it's not as easy to implement as you might think. It takes a little bit of work. Okay, another question from Anant. With regards to the MCML and MCXYZ slide, when performing simulations of light transport in tissue, it assumes biological values obtained from measurements. However, depending on the disease state, medication, and other factors, don't you think these values will change? How can we factor these into our simulations? Excellent question. In fact, that is the whole important work of biomedical optics, is to understand the relationship between observables, like a transmission measurement or a reflectance measurement, a wavelength dependent measurement, and the underlying theory that can predict that behavior, because then you get some sense of the structural changes or the chemical, you know, absorbing changes that are going on in the tissue. Okay, before going on with any more questions, let me just check in with Martin and Aaron. Are we doing okay? Martin, I lost your picture, so I just want, has everything been moving along okay?
Yeah, you're doing a great job, Steve. I'm just listening here quietly, and as I'm sure most of the students are. So
okay, so
you're doing
we
a really
sort of
great
got
job.
we sort of got started. I'm trying to time this. Actually, the tissue optics part is actually one of the most important sections. So I want to sort of devote the full half hour to that.
Okay.
And then we can always shorten some of the others to keep us within the time frame. So if everything's okay, I'm going to go on to the next question.
Yeah, so if you'd prefer us to read them to you, that's fine, but I think you're doing a good job as you go.
Because I'm sort of editing the questions to state them in a proper form. All right, so now I have a question from Raymart J. Canoy. In lecture 2, can you please explain how will the behavior of the reduced scattering coefficient change when you alter the reference wavelength from 500 nanometers to another value? The answer is there'll be no change. So if I choose 500 nanometers and then I calculate what the scattering would be at 500 nanometers, that's the quote A, that A to the lambda minus over 500 nanometers to the minus B. The A would be the value at that 500 nanometers, the value of the reduced scattering coefficient. And then the lambda over 500 to the minus, let's say, B power, at lambda equals 500, it's 500 over 500, which is 1. 1 to the minus B power is 1. So you just get the answer. If I was to have used 600 nanometers to reference, then my A would be the value at 600. And then within the parentheses, lambda over 600, when I get to 600, becomes 1. And therefore, the answer is the correct answer at 600. In other words, it's not going to change you can use any reference you want. And you'll end up with the net result being exactly the same. Okay, David McMahon asks, could you please describe the intuition behind predicting that the color of gums would be orange were it not for the multi-layer system? Okay, this was mentioned in the talk, that if I had a homogeneous tissue that had a mixture of scattering and blood, then red light would go in somewhat deep and come back. It'd be a strong reflectance of red. Green would go in a little bit, medium, and come back, and there'd be less reflectance because green is absorbed somewhat by blood. And then the blue would go in a little ways and come back, but because it's so strongly absorbed by the blue light is so strongly absorbed by blood, it would be greatly reduced. So you'd have red, orange, and blue. And that gives you an orange color. Red, green, and blue. And that gives you an orange color. Now, if you have a 2-layer model, the blue light, which is only going superficially, will be largely reflected from the bloodless layer. And only a little bit will have gotten down and peaked at the blood that's at in the lower layer. So the blue will actually be less absorbed, and so the reflectance will come up. In skin, I call this the epi-blue factor, because only at very short wavelengths, around like 420 or so, do you actually get a higher blue reflectance than the homogeneous model would predict. And so now you have red and then equal green blue. Well, that's pink. So that's the basic idea. Aiden asks, can everyone see the screen share? Yes, we're past that. Everything seems to be working now. Let's see, Anonymous. In the example of the Monte Carlo model for skin with 5 layers, why is the scattering coefficient at 500 used while working with multiple wavelengths? Well, we sort of talked about that before. You could use any reference. The net result ends up being the same. Let's see, Martine Cooper asks, has there been any study investigating a reference range for healthy people? If not, how can you be sure about the values of of absorption and scattering in different states of health and disease when it can differ so much per person. Well, you're absolutely right, Martina. Absolutely right. As far as healthy people go, we look at the literature and you put together, you know, your best estimate based on everyone's work as to what a typical tissue would be. And I've written a review on that. I think that was given to you. So there, yes, there is sort of an average value for healthy people out there, but even healthy people vary a lot. So, you know, it's very ballpark to come up with an average number. You can use it when you're trying to design things, but really there is no average. Well, there's an average number, but there's a broad range, even for healthy people. And then when you get into health and disease, this is absolutely why we're doing this, so that we can detect changes. And there hasn't been enough work, I think, on cataloging the changes in optical properties for various conditions of disease or pathology. So that's still the future of where a lot of work still needs to be done. Largely, we look at changes in absorption due to blood, because you get erythema or you get angiogenesis around a tumor. We look at changes in water in a tissue because there's edema or desiccation that may be going on. We look for changes in scattering because there could be fibrosis. For example, around a tumor, there is a increased fibrosis that occurs. And so that is an indication of a tumor that may actually metastasize. Hydration itself may affect the scattering. So there's a crosstalk between edema and scattering. In general, remodeling of a collagenous tissue involves breaking down fiber bundles and then rebuilding fibrils into new bundles. That can cause a change, a shift in the size distribution of fiber bundles within versus fibrils within a tissue. That can be seen with scattering. So all that still needs a lot of work. Okay, Wahat Hassan, you mentioned that scattering reduced the mean free path, but in NIRS, as we increase the source detector distance, we get more depth, and obviously the scattering is also increased. Can you please talk? Okay. It's true that if you have a source fiber and a collection fiber and you move them apart, the banana that shaped pattern of where most of the light is going from the source to the collector, that banana will increase in depth. My experience is that as you go farther and farther away, the maximum depth of that banana is about 1/3 of the distance between the two fibers, crudely. You say you get more depth, and obviously the scattering is also increased. Well, let's be more clear. The number of scattering events has increased, but the scattering coefficient has not, because that characterizes the tissue. So a property characterizes the volume, but the volume itself is an extensive variable, just like the number of scattering events would be an extensive variable rather than an intensive variable like an optical property. Okay, let's see. Ricky Xian says, I mentioned that Rayleigh and Mie scattering differed in their wavelength dependence. Why exactly is Rayleigh scattering wavelength dependent and Mie scattering is more wavelength independent? Okay. So let me explain. There's two aspects to scattering. There's the strength of scattering, and then there's the wavelength dependence of scattering. As you go into Mie scattering, the wavelength dependence of scattering is more of a lambda to the -1 power, roughly, or a little less, lambda minus 0.5. It's in that ballpark. Whereas Rayleigh is lambda -4, so it greatly favors blue light scattering. But then you have a multiplier, which is the strength of that scattering. And the strength of scattering also changes with the wavelength that you're using. So how to put this? You've got, well, the real good example I talked about in the lectures were the nuclei. So Min Xu from CUNY in New York has published on this, that as you move to longer wavelengths, the anisotropy seemed to become more forward directed, even though at the longer wavelength, all the scattering of the tissue should look smaller and smaller and smaller, and therefore it should be more Rayleigh-like. Why does the G value increase rather than decrease as you move to longer wavelengths? And the answer is, as you're moving to longer wavelengths, you're approaching the size of the nuclei. And the nuclei and the chromosomes are very big, and they scatter in a forward direction. The efficiency of scattering goes up as you match, as your wavelength matches the size of the scatterer. And that's why the nuclei start to dominate the anisotropy as you go to longer wavelengths. And that dominates over this effect of the smaller. So the point is that me scattering is wavelength independent, but it depends on how well the wavelength matches the size of the particle. I'm probably not answering this completely well, because this is kind of a complex question to approach. So I'll leave it at there. And I think that's an inadequate answer, but I'll have to move on. Let's see. Wahad Hassan asks, is there any way to increase the anisotropy to avoid backward scattering? Well, not something that you can do experimentally. Let's see. Obviously, if you again, scattering involves both a wavelength dependence and a magnitude. And the magnitude is very sensitive to the refractive index mismatch. So if you were to index match a tissue, for example, putting glycerin on skin such that the glycerin goes in and alters the skin so you have more matched conditions, or a tissue, more matched refractive index conditions, you end up with less scattering in general. So yes, it is possible to lessen both forward and backward scattering by index matching, by adding something like glycerin to penetrate into a tissue, or sugar solutions will do that, very thick sugar solutions. Okay, Subhasri asks, the average blood volume fraction of skin is supposed to be very low, maybe 0.2%. How is this average value calculated? Considering a large amount of blood, 2 to 5% is concentrated in the reticular dermis. Is there any formula or approximation to calculate the average fraction 0.2%? Okay, so the 0.2% number comes from actually making measurements and comparing to theory. And the only way a theory matches the experiments is if you say that the blood volume fraction on average in skin is very low, like 0.2% is a reasonable number. It can vary from 0.1 up to 0.4 easily, but it's very low. It's less than 1%. But if you go to other tissues, like you go to the gums and you get up into the 3 to 5% blood concentration, and if you look at tissues like the brain, it should be more like 5%. So yes, there are tissues that have higher blood content, but in skin, which is largely a collagenous, cell-free tissue that is actually just leather designed to mechanically protect you, there's not a lot of need for a lot of blood flow. The only blood flow needed is to feed the superficial vessels that feed the epidermis, and that's a very low blood volume. So you end up with a low average blood content in skin. Okay, Angun Arisev asks, how are the dipole arranged in biological tissues typically? Are they oriented in a particular direction? Okay, so in some tissues, there are orientated fibers, like in striated muscle, or in nerve fiber bundles in the brain. But besides those two examples, most tissues, the scattering elements, the scatterers in a tissue or a cell, are randomly oriented. Now, when light propagates, the electric field of an optical wave propagates through tissues, through cells, the electric field causes a separation of charge. It doesn't really matter what the orientation of the molecule is. In general, there's a separation of charge. Depending upon the molecule, there may be more in one orientation than in another. But if you have a population of molecules with random orientations, there's a net average charge separation. And that's independent of orientation of the population. So I wouldn't say that there's an orientation of dipoles in general, only in those special cases. Okay, Maria Yu asks, when comparing an image of light propagation through a tissue, the effects of the change of index when getting into a tissue are clearly observed. In order to simulate this change of index in the propagation, would Monte Carlo be a better option than diffuse modeling? Well, let's see. An image of light propagating through tissue. I'm not quite sure what that means. If you're just saying a transmission image, having send light through a thin layer of tissue, or if you're saying a reflectance image from a tissue, you're going to end up with different answers. In general, if there's only a few scattering events involved, then Monte Carlo gives you the proper answer. Diffusion theory is inadequate. If you're looking at multiple scattering, so you're propagating through a thick tissue or you're doing reflectance from a thick tissue, most of the light is going to be diffuse. Now, there's special cases. If you do a polarization image where you deliver linear polarized light, you take two images, one parallel and one perpendicular, co and cross polarized images, the two images will almost look the same, but if you take the difference, there's a little bit more light in the co-polarized image. That's because the co-polarized photons have only propagated very superficially and then kicked back and still retain their polarization. Whereas 90% of the photons coming back have multiply scattered. They've gone deeper and multiply scattered. So those are properly modeled with diffusion theory, but the very superficially scattered light is modeled by Monte Carlo. Okay, let's see. Those are all the questions I have on the list. So I'm going to turn back to Martin to ask what's next.
Yeah, thanks so much for that, Steve. So we've had some other questions come in while you were answering those. So yeah, there is a lot of interest in your lectures, and I can see that people are very excited about the opportunity to ask you these questions. Obviously, we don't get the opportunity to have this kind of interaction very often. So I can start by reading some of these out, and perhaps Adon in the meantime can email you the next list.
Okay, do that.
Yeah, so the first one I see, well, let me go back to the top. Here, just give me a moment. So it may be that you've answered some of these already, but let's see.
Go ahead.
One from Julian Tampu. So he's asking 2 questions. Using Monte Carlo simulations, we can get a good picture of how photons propagate inside the tissue. My first question is, can we perform a large number of Monte Carlo simulations to create a lookup table that can later be used to match, in inverted commas, a set of measured data with simulated tissue structure? So do you want to answer that first, and then I'll hit you with the other one?
Yeah, sure. Let's see. I have this. Let me share my desktop, okay? To
Sure.
answer this. So I'm going to share my screen and go to here. I had these little summary of tissue of
We're
results.
seeing your screen, so that's good.
Yeah, but I want to. I'm looking for. Oh no, I didn't put it here. I'm sorry. Let me open up the. To be tissue properties, optical properties, lecture on measuring optical properties. Here it is. Okay, so then somewhere down here, I discussed the concept of making a measurement with a fiber contacting the tissue. And here, let me put the screen up completely. So here you have light being delivered, and then immediate scattering coming back into the fiber itself, which can be measured, or you're measuring the total reflectance that's gone deep. So you get 2 measurements, your fiber measurement directly under the beam and diffuse reflectance. And when you put those 2 on a grid, so running Monte Carlo, just like you said, and putting in a value of G1 for this anisotropy and G2 for that balance between narrow versus broad scattering functions, you can then run Monte Carlo with these set of optical properties, and you'll get different answers for the measurement directly under the fiber versus the measurement of diffuse light, and you end up with a grid. So now, if I was to make a measurement of diffuse light that was 50%, but my reflectance was maybe 0.3 times 10 to the 4th per centimeter squared, I'd be here. And I would say, well, I have a G of maybe like 0.6, a G1, but my G2 is around 0.65. That's kind of a very broad scattering. And then what if for my 50%, instead my fiber gave me more like 1.3 times 10 to the 4th, clear up here? Then I'd say, oh, gee, that must be a very narrow G2 scattering function. And I'm also a little bit more forward directed. This is a double Haney-Greenstein function. The point being that 2 measurements can be predicted by assuming 2 parameters in the Monte Carlo and creating a grid. And once you have the grid, 2 experimental measurements can come back and explain what the G1 or G2 in this case might be. And so let me quit the screen. I think that's quitting the screen. And so now I'm back. Is this correct?
That's great.
Great. So
follow-up.
Go ahead.
The follow-up question was, if this is possible, what do you think of training a deep learning algorithm with the simulated tissue structure and the results of the photon propagation in it to do the matching between the measured data and the tissue structure?
Okay, so very good question. So when you get into the issue of machine learning, and I'm not an expert, but I've dallied in it. I've played with it. And of course you can do lookup tables, and that actually works quite well. But you can also do machine learning, and I've done the simplest of machine learning, which is nonlinear regression. So I'll end up with, let's say, a choice of blood content and oxygen saturation, and maybe scattering, maybe melanin. So I'll have a set of maybe 4 parameters I'm interested in. I'll set those parameters, put them into the model, calculate the spectrum. I'll do it for several wavelengths. So I'll end up with a spectrum of reflectance, and I can convert that into, well, I can then take those wavelengths I've let's say there's 7 wavelengths I calculated based on these parameters. Those now are my experimental measurements, and these are the underlying parameters. I then do it again and again and again, where I'm randomly varying my blood and oxygen saturation, etc. And I make many of these entries into a big table. Now I end up with essentially 2 matrices, a matrix of all these underlying parameters and a matrix of all my observations. And then I can solve that matrix equation for the coefficients, which when they multiply the observations produce the underlying parameters. And you can solve for the coefficients that work for all the entries, and you end up with a solution. So that's the simplest of machine learning. And I've done that, and it works, and that is a very appropriate way to proceed, because you pre-invest your time doing all this work. But once you're done, you have a solution that very quickly can work. So it is a very good approach. So that's a brief statement.
Thank you for that, Steve. Next question. In the graph of scattering coefficient versus the wavelength in lecture 1, why do we see multiple lines per material? For instance, multiple blue lines for water.
Okay, I'm going to once again share my desktop here, and I'm going to go back to
so lecture 1. It was 18 minutes in. So
right, yeah, but I had it in my summary picture here. So, oops, not that one. Sorry. Question and answer period. I had that picture here. So this is the picture I believe you're asking. Why are there multiple wavelengths? So, or lines. So here I'm going from 10% water up to 90% water. So you kind of see how a broad range of water changes the absorption coefficient. And here for blood, I'm going from, I forget the number, but it might have been like 0.1 up to 0.01 up to 0.1, maybe. I forget. Maybe it was lower going up, but it was a realistic variation of the amount of blood that might be in a tissue. So I've added the blood to the water. So this increase is due to blood, and here the increase is much more modest, and here it's very negligible. So adding yellow pigment on top lifts it some more, fat, and then adding melanin lifts it even more. So that's what I mean by this. These ranges are realistic amounts of melanin, of blood, of pigment, yellow pigment, of water. And over here, this is increasing amounts of me scattering, and then increasing amounts of Rayleigh scattering on top of it. And in the original slide, I had numbers in here. Okay.
Okay, so Luis Alaman Castaneda wanted to know, do you ever have to deal with more general scattering anisotropy, not just the cosine theta distribution, but also in psi, according to your nomenclature?
Well, I'm not quite sure what the question is. I would say that that we have more recently developed the MCXYZ to include refractive index differences in all the voxels so that we can have inside a tissue a structure with a different refractive index. And so we can now account for the reflectance, the specular reflectance, if you will, off of refractive index boundaries within the tissue. Another aspect of your question might be more general scattering rather than Henny-Greenstein. And most recently I've been working with the Gegenbauer scattering function, which looks similar to a similar to a Henny-Greenstein scattering, but only when one of the parameters exactly equals 0.5 does it collapse to the Henny-Greenstein function. So in other words, I'm attempting to create scattering functions which are more broadly variable than just a Henny-Greenstein. And there's a whole literature of people who have tried to do this. And I also include a double Gegenbauer. So I've got both forward and backward scattering combined to give a net, more complex scattering function so that I can explore the ability of light to multiply scatter to a focus and to study how the reflected light from the superficial layer that goes into a microscope depends on the scattering function. So I'm in the midst of still working on that, and there are other people doing that as well.
Okay, Atta Ghazari wants to know how we can model oxygen saturation level of the blood.
How can we
model? This is from your lecture 3, Monte Carlo.
Well, so the oxygen saturation is a parameter that is simply the ratio of oxyhemoglobin to total hemoglobin. So it goes from 0 to 1. And it's simply a parameter that describes the situation. Now, in reality, in a tissue, you've got arterial blood coming in, and it's highly oxygenated, maybe 0.97. And then you have capillaries, and then you have venules leading to veins. And the veins may have a very low oxygen saturation because the tissue has pulled the oxygen out of the capillary bed. And so you have something maybe like 0.3 or 0.5 for the scattering, for the oxygen saturation in the venous side. When you look at a tissue, you're actually seeing a mixture of all of this. So for a moment, assume that the volumes of the arterial and the venous are the same, then you would get something between 0.97 and let's say 0.5. You're going to end up with something sort of like 0.7 or 0.75 as a mixed arterial venous oxygen saturation. One of the key questions, which I've not been able to find a good answer for, is what's the relative volumes of the arterial and venous side of the microvasculature? Is it always equal to 1, or is it shifted? And certainly in some situations, like Port Weinstein, it's shifted toward the venous. So that complicates the interpretation because you need to understand the volumes in order to interpret what the mixed measurement of oxygen saturation, how it pertains to the amount of oxygen being pulled out of the capillary beds. But that type of modeling can treat the issue of microvascular oxygen saturation. Okay.
Wajahat Hassan asks or says that you mentioned the scattering reduced the mean free path, but in NIRS we increased the source detector. We did. Okay. I think maybe there's a bunch of these that we've already answered, probably. So does somebody know how we get to the ones that we haven't answered yet? Let me go to the bottom.
We've been going for quite a while. We were supposed to start at 6, and let's see, 6:30, 7:30, 8. We've gone for an hour and a half from the original time. So I'm wondering if people need a break.
Yeah, we can do a break. Some of the questions are to do with the next lectures.
I don't need a break, but it's just, why don't we just take, maybe let's take only a 10-minute break so people can go, briefly away, and we'll resume in 10 minutes, okay?
Sure, let's do that.
Perfect.
Okay, so we will ask people to come back. Well, why not make it 4:20 UK Irish time?
Okay.
So, if people want to figure that out, they can just look up time in Dublin. So
that's 13 minutes from now. 13 minutes
16:20.
from now.
It's about 13 minutes from now. Yeah.
Okay.
Okay, thank you, Steve, and thanks to everybody, and we will be back shortly. All right.
Hi guys, just so you know, you can just to mute yourself while we're on break if you want to talk, because the event will still stay live.
Okay. Well, I'm not going anywhere. But this seems to be working okay. Have you gotten any feedback from anybody by chat?
No, not yet, but I can ask for some feedback. I can make an announcement now.
Steve, do you prefer reading the questions yourself or having Martin read them?
Actually, Martin's doing a pretty good job, and I think it's more fun for someone else to read the questions and then I answer. The only advantage to my doing it is I can look at the whole question and I can dissect out what's really the key part, but that has not been a problem. So I would vote for letting Martin ask the questions. I think it's more fun for the viewers.
Yeah,
Okay.
and it gives you the opportunity. It's easier for you to share your screen that way than like you've been doing with a couple of slides.
Okay, so that's the way we'll continue. That sounds great.
All right.
People resubmitted
Can
their
somebody
questions.
send me a list of questions that have not been asked? How do I eliminate the questions that are already asked? Because we republished them, I think.
Well,
I
you
don't know.
just delete them.
Yeah, I don't know. Usually we were going to go through them before we publish them, but they're there now, so we'll just have to go through them one by one now.
Yeah.
Any new questions?
Okay, but we're not going to go through the ones we already answered.
Well,
Yeah.
I can tell you that the last question that I answered was from Maria Yu at 2:51 p.m.
Oh, it's just some people might, I think some people just put it in again because it's a new event, so they just type the exact same thing in again. So it's the timings are a bit different and the order is a bit different, but we can try go through them now. Adon, can you send me on that list that you have, and we can go through the published ones and delete the ones that have already been asked?
The list I have
of the questions from the first one.
Yeah, I'd send that.
Yeah.
Perfect. And then what we'll do is we'll leave.
It's nice to have a record of them, I suppose. Or will people actually be able to go back through this record, or they just, I don't know. Yeah, we can. I guess we can publish a list of questions one way or another, if necessary. We can think about that later.
What we can do is if Adon's sending me on that file now, so what we'll do is before we publish any of the things in the new, we'll check if they've already been asked in the previous one. So we're not publishing any already previously answered things.
Have you been recording the question answer period?
Yes, this is recorded.
Yeah, well then that's the way people should actually get this, is that they just watch that recording and they hear the questions and the answers. That's clear.
Yes, yeah. Perfect. We've some feedback here. So the first one is from Atta Shazari. She says, I appreciate the way Steve responds to the questions patiently.
You're doing a great job.
They're good questions as a rule. Yeah.
And the second one, the second one was just a question about a different thing. I'll reply to that.
How many people are online listening? Do you know?
86 at the moment. We hit a max around 110 a little while ago.
I'm curious, when it started at 6:30, how many people were signed up?
Yeah, I can take a look back at that actually later. I think we've the log sheet from the first one. At the beginning of the day.
Yeah, I regret the things that I wasn't able to get through earlier.
Oh yeah, no, we always knew there was going to be a snag somewhere, so at least it's at the very beginning. There's always definitely going to be technical issues somewhere along the way.
Okay, we have another 8 minutes. I think I'll stretch, so I'll be back.
Yeah, me too. So see you in a little bit. Okay, so do we know which questions to start with then? Where can I start, guys?
Well, I had a question. Can you hear me, Martin?
Yes. Mm-hmm.
Originally, that we were part 2 was going to be measuring optical properties, but I had suggested that the second one be Monte Carlo, and then the third be measuring optical properties. At this point, I don't know what the students were told, and really the way things are going, it's more dictated by the questions in a way. So I have my short little, just a less than 5-minute introduction to each of the sections, which I thought was worthwhile because it kind of reminds people of what had been discussed. But we didn't use that for the first session. Should we use that for the next session? Because it only takes 5 minutes. And do you want to start with Monte Carlo or tissue optical properties, or measuring optical properties?
Okay, so we've had a few questions about Monte Carlo, but I think that's okay. I guess we still have some more, and I'm pretty sure that your introduction will stimulate questions on Monte Carlo.
So why don't we go with Monte Carlo then? Because I think it makes more sense. So, all right, it's now 4:21, so we should go live, right?
Yeah, and but which questions? Where do I start, guys, in asking questions? Can I start with the list?
Well, I'm going to do my 5-minute bit.
Oh yeah, you do that, and we'll figure it out.
It gives you time to get some questions, okay? So I'm going to share my screen, and presumably all the students are back. Is that correct?
I think so. Yeah.
Okay. Hi, everybody. So what I'm going to do here is excuse me, is go to just show you a few slides by way of introduction of this part 2 discussion, which is going to be Monte Carlo simulations. So I had
2 seconds there now, Steve. I'm just waiting for your share screen to show up. It's just been a bit slow.
I see. Okay, so tell me when it's on. I believe I'm sharing it, but it says bad network quality. I could quit and try again.
Yes, do please.
Okay, so I quit. Now I'm going to do share desktop, screen, and go back here. So do you see that?
Still waiting. It's still just loading. Still waiting for it to show up now.
I can see Monte Carlo simulations on my screen.
And
yeah, I need to wait for it to load so we can send it to the students as well.
Oh, I see. I see. Okay. Yeah.
So the students are online listening to us talk?
They are, yes. Yeah.
Okay. Well, hi, everybody. While they're getting the picture set up, I can just tell you that this next discussion will be on Monte Carlo simulations. This is good because having discussed optical properties, the simulations let us discuss the details of how the optical properties affect the movement of a photon in tissue. So it's kind of the natural next step. And then part 3, we'll talk about measuring optical properties, because once we understand light transport, we then can say, how do we use light transport to go from measurements to optical properties? So that would be part 3. So if this is not going to come up, then we should just go to questions and answers.
What I can do is I can share it for you. I have your file here as well.
Oh, okay, let's do it that way. Okay, great. Okay, so everyone can see that. You might make it full screen, and
yeah,
then
will do.
And I'll just tell you when to advance. So here we're looking at the distribution of fluence rate, watts per centimeter squared, in a knee. This is the cross section of a knee where deep red light, 808 nanometer light, is being delivered to the knee. And you can see that the light is penetrating into the knee to some depth. Next slide. Next slide, Aaron.
Sorry, I don't think the students can see it still at the moment. It's still being slow. I think it's just Microsoft Teams in general.
I see. Well, we could just go to question and answer.
Yeah, we can try that.
Yeah, let's just do that.
All right. So that means, yeah, I should.
So stop sharing, Aaron.
Perfect. Yeah.
So here's a question regarding Monte Carlo simulations. In the literature, many parameters, scattering and absorption of skin, skull, dermis, and so on, reported are related to ex vivo or animal measurements. Do you think that if it would be possible to measure them in vivo, this could lead to different results? In this case, what is the most precise technique to measure them?
Okay, this is very good because it's right at the heart of the problem. If you make a measurement on an in vitro or ex vivo tissue, the first thing that's wrong is that there's no blood, or there may be some residual blood, but it's the wrong amount of blood and it's all deoxygenated, or rather maybe it's all oxygenated because there's no living tissue there to deoxygenate. The point being it's wrong. And the water content may not be right because you may have desiccated the tissue a little bit or overhydrated it. If you put it in saline to keep it, quote, fresh, actually it swells. It can swell. And so you end up with the water content being wrong. And then that can also swell collagen fibers, so the scattering is wrong. So basically, ex vivo gives you an idea of what's going on, but in vivo can really be different. And what would be the best way to do that? Well, I've been working on reflectance measurements of different sorts because I'm interested in non-invasive measurements that can be done in vivo that are not going to harm the patient or the subject. So I work either with reflectance as a function of distance from a point source of injection. That would be like a 2-fiber measurement where you vary the distance between the collector fiber and the source fiber. Or I've done work with microscopes where you focus to different depths in the tissue, and as you focus deeper and deeper, your signal drops out exponentially. An exponential has 2 parameters, a multiplier and the exponent of decay. And from those 2 parameters, you can map to the scattering coefficient and the anisotropy of scattering. So I learned something about scattering in superficial tissues with microscope measurements. I learned something about blood perfusion and hydration and scattering in tissues by multi-fiber measurements where I have different source collector distances. Okay. Next question.
I'll ask you
I muted myself, so I'm going to ask the question. Murali, can you tell us some other properties of light in addition to measuring polarization interference that can help us to have a better estimate of tissue properties, specifically towards multiple scattered light?
So I'm not sure of the question. You're going to have a scattering coefficient. You're going to have a deflect, which tells you how often it scatters, and then you have a scattering phase function which describes the deflection of the photon with each scattering. So those are the 2 parameters that operate, and you can talk about refractive index of a tissue, and when you get into optical coherence tomography or any type of interferometric measurement, the refractive index comes into play. If you have polarized light, you can actually monitor the rate of depolarization of light, which speaks to the birefringence in a tissue, or just plain the phase retardance that you may see for light delivered versus collected, and that can speak to the birefringence of a tissue. But I'm not quite sure what else you're fishing for in your question.
So, well, let's move on to the next one from Wajahat Hassan. If we use both polarized circular polarization and unpolarized light, which one would be best to achieve maximum depth?
Oh, well, the answer is unpolarized light. Circular polarized light does go deeper than linearly polarized light. And I'm not going to get into why. I don't have a quick answer off the top of my tongue, but it's just circular polarized light's a little more forgiving. So circular polarized light can penetrate more deeply before it is kicked back. And then when it kicks back, it actually switches its circular polarization from right to left or vice versa. But then it can get back. So compared to linear polarized light, circular polarized light is a little more deeply penetrating, but not a lot more. And diffuse light or non-polarized light, that's what can go in very deep because that's all diffusion based. So once you've lost polarization, you've still got plenty of time for photons to survive before they need to escape. So you've got much deeper penetration with unpolarized light. Okay.
Yeah. Can I just clarify there, Steve? So really we're talking about putting in polarized light and detecting it as polarized light.
Right.
If we put it in and we detect it as diffuse light, that can still go as deep as what you're calling diffuse light, right?
Yeah, if you put in polarized light and then you're just collecting multiply scattered light coming back, it really doesn't matter what type light you delivered.
Right, that's great. I just wanted to clarify that point. So Giles Blaney wants to know, how do various instrumental errors propagate into the measured data and recovered optical properties? For example, are there instrumental effects that could cause wavelength independent shift in absorption?
Let's see.
I guess we're getting at things like spectral sensitivity of the detectors and those kind of things.
Oh yeah, well, okay, those are so obvious that I wasn't even thinking of those. Yes, so you have a light-dependent light source, a wavelength-dependent light source, and you have a wavelength-dependent detector response. And so in the lecture on measuring optical properties, I showed how those factors can be canceled if you take a measurement on a tissue and normalize by a measurement on a standard, because the source and detector cancel. And now you get a measurement which still has a constant involved, because the geometry of the collection of the tissue measurement versus the standard measurement might be different. And there's a reflectance of the standard that fits into that equation. But the point is, that type of ratio of a tissue over standard measurement cancels the wavelength dependence of the source and detector. And that's very important. You have to do that.
Okay, maybe one other point is each layer acts as its own filter for the next layers. Is that fair to say?
Yes, and it's not just a one pass, like the first layer now affects the second, and then the second affects the third. No, the first affects the second and the third, and the second affects both the first and the third affects all three. They're all cross-talking all the way. So yes, multi-layered measurements or tissues are complex, and Monte Carlo, when you set up multiple layers in the Monte Carlo, will automatically handle this.
So the same person, Giles, had a question which is, I guess, related. Can you discuss the key things to think about when fitting a spectrum of reflectance to recover tissue absorbers and scattering parameters, and any pitfalls to avoid, specifically for the range between 600 and 1000 nanometers?
Let's see, I didn't catch whether in the beginning you mentioned the multi-layers. If you have multiple layers, then the analysis becomes a little more difficult. If you have a homogeneous tissue, then you're able to simply change the blood content, the oxygen saturation of the tissue, run Monte Carlos or diffusion theory, and get a lookup table, and you can figure things out. Because there's really only two parameters, let's say, blood and oxygen saturation in the one layer. If you have two layers, suddenly you have four parameters. You've got the blood and oxygen saturation in the first layer and the second layer. Or maybe you have absorption and maybe you have scattering as well. So then you've got this absorption and scattering in the first layer and the absorption and scattering in the second layer. You've got four measurements. Well, now you're going to have a four-dimensional lookup table suddenly in order to do stuff. It ends up getting, much more complex as you start to have multiple layers. So yeah, this is still an issue. I'm still working on efficient ways to handle this, but it is something that has to be dealt with.
Okay, Martina Kuiper has a question. What kind of calibrations are being done for measurements with DRS and other techniques gaining optical coefficients to be able to relate between different measurements and laboratories? It's kind of standardization.
So DRS is dynamic reflectance scattering, or what? DRS.
Maybe it's diffuse reflectance spectroscopy.
Oh, okay. There's so many names. Yeah. All right. So diffuse reflectance spectroscopy. So can you repeat the question? Because it was confusing.
Sure. So what kind of calibrations are being done for measurements with DRS and other techniques gaining optical coefficients to be able to relate between different measurements in laboratories?
Okay. Well, so I discussed this in the lecture on measurements, that if you make measurements with optical fibers, you should make a measurement of a standard from a given height rather than touching the standard, because then your standard has a known reflectance as a function of wavelength, which the manufacturer may give you. But if you touch the standard, you have to know both the absorption spectrum and the scattering spectrum of the standard, which usually you will not know. The manufacturer probably doesn't know. And so you can't calibrate by touching a 2-fiber probe to a standard. You have to be off of the standard. That's one thing. In general, though, when it comes to calibration, I routinely use Spectralon, but if I don't have Spectralon handy, I will sometimes just use a stack of white paper, because that usually gives me a reflectance of around 0.91 or so, 0.92. So I crudely calibrate, but basically you need a reflectance spectrum, a reflectance standard to make a measurement. When you start to do microscopic work and try to look at scattering, that's not very well developed yet, because now you're actually needing to know the optical scattering properties of the standard itself. So you can do this with, let's say, a gel that contains polystyrene microspheres of different sizes. You have to be very careful in preparing it such that you sonicate it so that your spheres aren't touching each other, and then get them well mixed in the gel so that you need it to be as properly mixed as possible. But then you'd be able to image, and you can actually image individual little spheres. And then you can look at how strong is the reflectance coming back from them. You can then use me theory to try to calculate what's expected versus what is measured. So that's one approach, but there's a lot more development of calibration standards for microscopy. Okay.
Okay, Hampus Munjeford is asking, assuming you have near unlimited processing power, is there still some downside, or are there still some downsides to using Monte Carlo compared to alternatives such as diffusion theory?
The only downside is time. The Monte Carlo methods are slower than diffusion theory, but as we work with faster processing units and parallel processing, actually Monte Carlo has become very rapid as well. So I would say that there's no real difference except in the accuracy. The accuracy of Monte Carlo near surfaces or near sinks, near sources, surfaces, and sinks is accurate, whereas diffusion theory is not. And so, well, it can be if you move up to higher polynomial fits, like the P3, P4, P3 type approximations. You can get P5. You can get closer to the boundary conditions, but in general, Monte Carlo is a very flexible way to approach the story near sources, sinks, or surfaces compared to diffusion theory.
Okay, so as long as diffusion works, then diffusion theory is better and faster, but
yeah,
thinner layers, Monte Carlo.
Well, and diffusion theory will give you an answer centimeters away from your source. Monte Carlo will have a hard time doing that. So unless you use some special techniques of sampling. So basically diffusion theory, once you get away by a couple millimeters from a source, depends on the optical properties, but then definitely diffusion theory works just fine.
Okay, Subhasri is asking, is the Monte Carlo code for the planar geometry applicable for a complex tissue anatomy such as the human head?
The human head. Well, to the degree that you can model the skin, the skull, and the brain tissue as planar layers, the answer is yes. So I would say that it gives you a pretty good first answer when you're talking about a point spread function. You deliver, let's say, a point source of light. That could be an optical fiber delivering white light. And then you're looking as a function of radial distance to a collection fiber. And that pattern of the point spread function extends over maybe only a couple centimeters, maybe 3 at the most. And on a head, you're still sort of in a planar situation. So I would say the answer is yes. As the first approximation, it should do the job.
Okay, Anonymous wants to know, how does Monte Carlo method yield reflectance? It just visually shows the light distribution, but how is it possible to have reflectance?
Oh, well, it gives reflectance. So when you run Monte Carlo, besides keeping track of photon deposition within the tissue, whenever the photon gets to the surface, it either internally reflects and stays in the tissue, or it escapes. And when it escapes at a certain position, a certain X, Y, Z position, or with MCML at a certain R distance from the source, and it escapes at a certain angle of escape. So the Monte Carlo can record both that position and that angle of escape. And then when you're all done, you have all of this escaping weight that has come out. You normalize it by the number of photons you delivered, and now it becomes the fraction of light relative, the fraction of delivered light that escaped at a given position at a given angle. You add up all the angles and you add up all the positions, you get the total reflectance. You add up all the angles, but keep the distance information. You've got the spatially resolved reflectance. And if you add up all of the spatial domain of that matrix, but keep the angle, then you've got the angular reflectance coming out, which if you observed from a distance would be goniometry, showing you the angle dependence of escaping flux. So basically, yes, Monte Carlo keeps track of escaping light.
Very good. Ale Sudaku, you assume a homogeneous semi-infinite medium for the estimation of absorption and scattering. Two-layered model is possible, for example, with time-resolved NIRS, where absorption and scattering are estimated in each of 2 layers. Could you speculate what is the maximum number of layers for which the absorption and scattering can be estimated? This is related to the maximum resolution that can be achieved in estimation of optical properties in tissues for monitoring absolute values or changes in optical properties.
So let's suppose that you have a tissue that has varying optical properties. Let's just say we have planar tissue, just to make this discussion simple. And you've got a whole bunch of layers going down. And the optical properties at each layer are slightly different. Well, then you could run the Monte Carlo for a distribution of properties, and you would get a result. If you then slightly increase let's say the absorption of just one layer and ran it again, you'd get another result. You'd have to have run enough photons that the 2 numbers you get are statistically different, so that if you take the difference, you know the perturbation that occurred by adding absorption to a given depth. And you could do that for each of the depths. So you'd get essentially what is called a Jacobian, namely, how much do you perturb a measurement when you slightly change just one of the elements? In this case, one of the absorbances at the absorbance at one of the layers. And once you have that vector of Jacobian, you then could approach the problem of peeling the onion. Ultimately, what you're doing is you're trying to say, well, what's the reflectance? How is it dominated by the first layer? And then the second layer is the combination of the first and second layer, and the third is the combination of the first three layers, etc. Except that actually all layers talk with all layers. That's why you have to really use a full matrix approach. So to answer the question of how many, how fine can your resolution be, you get an increasingly large matrix to unfold as you do this problem. And it really, from experience, I believe it becomes difficult when you have too many layers involved. If you have a model for the general pattern, like you think that it's going to fall as an exponential in some property, then it's much easier to try to take a set of measurements and determine the depth distribution of your properties. But this is all from the modeling point of view. If you actually do an experiment, you're kind of stuck because you're just making a measurement. You can make measurements maybe with like R of R measurements, source detector distance being varied. And that gives you ability to do a depth dependent set of measurements, and then that can be resolved. But there, my experience is that such type of diffuse light tomography, you're limited to, let's say, on the order of 5 millimeters, actually resolving structures. But that could vary with optical properties and wavelength. So I don't have a quick answer for you on that. Okay?
Yeah, okay. So Giovanna Paranjos wants to know, is the scattering affected by the presence of preservatives such as formaldehyde, and how do you account for it?
So formaldehyde, I believe, definitely affects scattering, but I haven't looked at that literature for a while to know if it makes it go up or down. Basically, you're cross-linking the scatterers, so it comes down to what degree does it cause increased clumping of scatterers or not. And if you increase the clumping, you'd actually reduce this overall diffuse light, or the anisotropy would increase because you got bigger structures. There'd be more cooperative scattering from the larger structures. So if cross-linking caused scattering structures to coalesce, then I would expect the overall scattering mu sub s prime, the reduced scattering coefficient, to actually decrease. That would be my guess, but you'd have to look in the literature to see what is going on. I haven't done that for a while.
Would you also have a refractive index matching effect, because it's much higher than water? It's 1.55, I believe.
Oh, well, if you were to put a bunch of formaldehyde in and leave it in, yeah, probably you would have a refractive index matching issue as well. I was thinking you would cross-link it and then maybe it got washed out. But yeah, if you just put it in, then you've changed the refractive index. It's like putting a sugar solution in. Okay.
The next question relates to lectures 3 and 4. Should we just go for it or leave that for later?
I think that it's just fine to go for it. So,
okay. We learned about 2 different ways of simulating propagation of light in tissue, Monte Carlo and diffuse theory. Is there any preference in using each one depending on the scattering regime of the tissue, me or Raleigh?
So that's a question about so I'm not quite sure where that question's going. You've got scattering. It has a wavelength dependent behavior. You can observe that. You can make measurements and just document, oh, this tissue scatters as mu sub s prime of lambda wavelength as sort of an A lambda over some reference lambda to the minus B power. Fine, there you are. Now you can say, well, why is it that? And perhaps you'd like to break that down more into A times lambda to the minus 4th power times a fraction plus 1 minus that fraction times lambda to the minus 1 power, or a me scattering value like 1. So if your curve can be fit by just an A lambda minus B, great. But if you have a little more Rayleigh scattering, then that function may not fit perfectly, and you may want to go to a lambda minus 4 plus lambda minus 1 type of fitting. Within the range, most people make measurements like up to 1,000 nanometers, like 300 to 1,000 nanometers, maybe 400 to 1,000 nanometers. A lambda minus B actually works just really pretty well. But if you then try to propagate out or predict what would happen at longer wavelengths as you move into the deeper near IR and into the IR, then the A lambda minus B can give you really wrong results. And that's where having the Rayleigh and me fractions are better, because once you get out to long wavelengths, it's all the me scattering. The Rayleigh scattering has nothing to do with your observed scattering. And so it's better to have fit the region of observation to a Rayleigh plus me, because then you have the ability to predict the longer wavelength behavior. Okay.
Meng Li wants to know the method you presented to estimate the sample's absorption and scattering coefficient by comparing the reference values. What would happen to the estimated absorption and scattering coefficients if the light source is copolarized or depolarized? Would the coefficients remain the same?
So it depends on the measurement you're making. If you're making a measurement of, let's say, delivering light at one spot and then looking at the light from a distant spot, you're going to have the light that you collect being multiply scattered. And so then a simple unpolarized light transport theory will work just fine. If you're actually making a camera measurement, so you're sending light in and you're doing co or cross polarized imaging, there'll be a slight difference, because the delivery of light at a spot entails a certain amount of reflectance from the very superficial layer, which is still unpolarized, whereas 90% or so of the light goes in deeper, multiply scatters and comes back. And so half of it goes into your copolarized image, the other half goes into the cross-polarized image. So the copolarized image has that one half of the diffuse light image plus that superficial, what I call subsurface glare, G-L-A-R-E, glare, subsurface glare. That is the still polarized component scattered by the superficial tissue. So it depends upon your measurement.
Okay, Hampus has another question. In the drawings on the slide, diffusion of light in lecture 2, you are showing 1 mean free path and 10 mean free paths. The former is utilizing the longer steps of 1 over mu s prime, while the latter is using the small steps 1 over mu s. Does this result in difference in path length of the medium? Multiple short steps to the same point will be longer path than one long step. That's not accounted for in Monte Carlo or diffusion theory, question mark. If so, is this something that could be relevant to correct for with some scaling factor?
Well, that's actually a really good question. So if I can paraphrase, if you launch a photon into a tissue and you take a bunch of little steps and the photon meanders around and eventually gets over to a spot, or you take one big step that looks like a nice straight step, the path length involved in those two is different. And so that you raise a really good point of confusion by bringing that up. My answer to that would be that the analysis by Monte Carlo would actually really track the overall path of the photon, and hence give you a proper Beer's law attenuation when you finally arrived at some particular point. The diffusion theory, which takes that big step, will have taken that step, but it will automatically have also assumed a path length that is tortuous going across that step. So it doesn't apply Beer's law to that big step. It applies attenuation based on a step that's much larger due to the multiple scattering. So you're not applying Beer's law to that big step in the random walk. And that's the difference. Monte Carlo is applying Beer's law to every little step. Diffusion theory is automatically accounting for the multiple scattering when it takes the big step. So you get the same answer both ways.
So Valeria Grasso is simulating photoacoustic images, and as a first step using MCXYZ scripts in order to simulate light fluence distribution within a 3D tissue domain with a depth of about 2.5 centimeters. This includes absorbers at different depths within a standard tissue and light at different wavelengths. On top of the tissue, she has an 8 millimeters of water to mimic gel for photoacoustic imaging. I noticed that only if the light source is positioned at the water tissue surface, I have a reasonable distribution of light fluence in depth. And instead, when the light source is on top of the water layer, the simulation fails. Could you please explain what's happening at the photons at the interface, to the photons, I guess, at the interface?
Okay, well, I'm not quite sure how she implemented that, but if one had a water or gel layer on top of a tissue, and then within the tissue you can have whatever you want, like a buried blood vessel, you can send light through the water. It'll enter the tissue, diffuse down to the blood vessel, absorb, generate a energy deposition. And then you can use a separate subroutine which will take the energy deposition and calculate how pressure waves would come back out to the surface to be collected. What I heard in the question was that you don't see any fluence in the region of the water above the tissue. I hope I got this right. And I'm not quite sure where this question was leading. The Monte Carlo can give you the fluence in the water as well as in the tissue, because even though the absorption in the water is very low, it's not zero. And when you divide by the low absorption of water, you get back the fluence. So you can actually document the fluence in the water, both what you delivered and then what escapes. So I'm not quite sure, and then that doesn't matter because that's just the light. What matters was the acoustic signal coming out, and that was a separate module. That's not Monte Carlo. That's taking the result of the Monte Carlo and using it in a pressure wave propagation. So I'm not quite sure where that what that question.
Yeah, my impression is it has something to do with the light source being in contact with the water or not in contact with the water. But presumably,
well, that really shouldn't matter. It really shouldn't matter because the light's going to get into the tissue regardless. So I don't quite see why that matters.
Okay, shall we move on, and perhaps Valeria can follow up later. Maybe Adon or yourself could try to help answer that question or follow it up. Christian Fernandez is asking, in what situations would you prefer to use diffusion theory over Monte Carlo? Similar to a question we got before, I guess, when modeling perturbations in a multi-layered system where layers are of the order of millimeter in size.
Well, I would say that that if I was, for example, doing skin, skull, and then brain, where you've got multi-millimeters involved, I would use diffusion theory because it's more efficient, and it would it would give you an answer that's very close to what you could get if you went to the trouble of doing Monte Carlo. So I guess my answer is I would use diffusion theory. But it depends on what you're doing. And if you were making very close measurements, then you'd probably want to consider Monte Carlo. But close measurements, what's the definition of close? And if you're a couple millimeters away from a fiber of delivery, then it may be that diffusion theory does just fine.
Okay, Giles Blaney has another question. Do you have any recommendations for Monte Carlo software with frequency domain or time domain capability, either layered or voxelated?
Okay, well, a shout out to Giles and to Christian. So I approached the problem of time resolved Monte Carlo back in the very beginning of my work in this area. So you can do a time resolved measurement of light transport, easy enough. You can get a point spread function for the time resolved response at some point of observation. So you now have a plot of, as a function of time, how your signal changes at that point. Now you simply take the Fourier transform and you move into the frequency domain. And I had used this to explore the difference between a Monte Carlo based frequency domain answer and a diffusion theory based answer. And what I found was that if you move too close together, then there's definitely a difference in the answer between the diffusion theory and Monte Carlo. And because it's becomes a very quick difference because it's so close, when you take the Fourier transform, it sends error throughout the entire spectrum. So you end up with a broadband frequency error when you get your two detectors too close to each other. An error if you use diffusion theory. But as long as you get a couple millimeters away, few millimeters away, then diffusion theory and Monte Carlo in the frequency domain give exactly the same answer. And so diffusion theory is just fine for the frequency domain measurements.
Okay, Giles, again, can you speak to the practice of running Monte Carlo using the reduced scattering coefficient as the scattering input with G equals 0, the advantages and disadvantages?
So you can do that. And the answers you get will be very wrong within the first, within a hemispherical shell that's the first few millimeters, first millimeter at least, maybe 1 over mu sub s prime, double that. So 2 over mu sub s prime. In that regime, you'll have a wrong answer. But beyond that, you'll get the right answer. So I don't know what the advantage would be. Yeah, I'm not quite sure what the advantage would be And yeah, I don't see an advantage.
All right, I'm not sure if some of these questions were asked before. Wajahat wants to know, is there any way to increase the anisotropy G to avoid backward scattering?
We answered that one.
Okay, and the one about the 500 nanometers, I think we've answered.
Yeah.
Do the guys know if we've answered all the questions? Jump in and let me know, please.
Hi, no, I have a couple more. I have a couple more.
Go for it, Arwen. Why don't you read them?
Okay. The first one I have here is from Ashwini, and would like to hear about your rationale behind regularization parameters choices in numerical reconstruction.
Okay. I have used the Tikhonov method for regularization when I've tried to do 3D tomography. So I've done calculations where I would have a 2D array of sources and detectors, and then using Monte Carlo, I can document essentially the Jacobian. I can document what would be the perturbation for every voxel position between any source detector pair in this matrix of measurements. And I can set up that as a matrix such that I take all the voxels, which are a 3D array, but I turn it into a linear array. That's my unknown of delta absorption expected. I have a background optical properties, and then I'm adding a delta absorption. That's my vector of unknowns. Then I have the matrix, which is this Monte Carlo generated Jacobian, so to speak. And then I have my observation matrix, which is the set. It's a linear array based on this 2D array of sources and detectors. So I have a matrix. Perturbations times matrix gives you observation at the fibers. You can then use the Tikhonov method to modify that to allow the ability to invert the matrix and make a measurement. So that I use the Tikhonov method for that, and there are limits to that. I've been able to image a blood vessel down to about a depth of 5 millimeters when I have an array of detectors across the top of the tissue and an array of detectors on the bottom of a tissue. So like with a clamp holding a piece of tissue and there's a blood vessel in there, I can actually locate the blood vessel when I have maybe, let's say, a centimeter thick tissue, not even that much. My ability to image is really limited to about 5 millimeters depth. It's been my experience anyway, and it depends on wavelength. And that's looking at a blood vessel. So my answer is I use the Tikhonov method.
Perfect. The next one then, I won't skip your praise either. Ashwini, same person again, says many thanks to Steve for your dedicated efforts to open interactions. The next question we have then is from Martine. She asks, is it possible to use Monte Carlo simulations as a way to characterize the uncertainties in the setup when measuring a reference in addition to using it to measuring tissue properties?
So I'm not quite sure of the question. So let's say I'm making a measurement and I make a measurement on a standard. I may want to understand what's the error in my measurement of the standard, because ultimately I'm going to make a measurement on the tissue and there'll be lots of uncertainty. So at least with the standard, I could ask the question, how uncertain is my measurement on a standard, which is presumably known? I think that's the question. And my experience on that is that it depends a lot on the standard. When I've worked with polyurethane standards where we put titanium dioxide suspended within the resin and created a polyurethane scattering model, we obtain really uniform scattering. And you can actually look at the reflectance from different spots and see a very, very uniform, error-free type of measurement. If you work with something like Spectralon, which is a standard, really Spectralon is like a white material with flecks of carbon, I think, but black embedded in it. And if you do microscopy of a Spectralon standard, you'll actually see a medium that has little points of high reflectance where the little black carbon, I think it's carbon, is backscattering within the medium. In other words, it's heterogeneous. And if you actually were to if you make an image of a Spectralon standard and analyze how uniform it is, it's not that uniform. So the thing about Spectralon, I like it a lot, but I use it for a kind of a total reflectance. If I do microscopic work, Spectralon has too much variability over the face of the Spectralon standard, and I would go with a polyurethane type of, or some other type of standard.
Perfect. The next question we have comes from Luca. He asks, "Dear Professor Jacques, what do you think about the reliability of comparing results from different techniques? For example, spatial frequency domain imaging and time-resolved diffuse optical spectroscopy for the characterization of MUA and MUS prime?"
Well, so they should give the same answer. If you have a homogeneous tissue, they probably will give the same answer. Certainly if you've allowed multiple scattering to occur. When you have measurements very close to the point of entry, then it's possible that the signal to noise for one measurement versus another may differ. Details may be a little different. So I would always be careful whenever I'm trying to make superficial measurements or very close to a source type of measurements. I would have to think carefully about whether different methods give you the same answer. If you're working with an actual tissue, which may have an epithelial or epidermal layer with an underlying stroma or dermis, then you definitely can see differences. But as long as you're away from the source, the measurement should give the same answer.
Cool. The next question then we have is, "Thank you for your lectures. I read a paper dealing with optical hemoglobin extinction coefficient data set for NIRS, and they said that the variation of hemoglobin extinction coefficients can cause 5 to 25% relative difference in the determination of hemoglobin concentration measured by NIRS. Have you considered the possibility of uncertainty? If yes, how to deal with the uncertainty? If no, what chromophore are you referring to?"
Well, first of all, if you go to our website, omlc.org, and look at spectra and look at blood and hemoglobin, you'll see a comparison of a variety of absorbers. Oh, go to my review paper that I passed to you, and I believe that's in there. There's definitely a handful of different measurements of hemoglobin absorption versus wavelength, and there is variation. But the variation isn't that bad. Certainly not giving rise to the 5 to 20-fold differences that you cite. So I don't think that's correct. Now, that's just between maybe 300 and 1,000 nanometers. As you move to longer wavelengths, there's not a lot of information out there. I certainly haven't found it. I used to have it, and that computer died, and that data was lost. I had measured that data with an old spectrometer, well done, and went out, to like 2,500 or so nanometers, and it was great. But what a shame to have lost that, but that was decades ago. I haven't seen a lot of good data, any really strong data, out in the longer wavelengths for hemoglobin in tissue. So in the more distant near IR, I can't answer your question because, you know, I don't know how variable the data you have in that range is. I would say though that even though people have done measurements on whole blood in cuvettes and made measurements, I've always been a little worried about what happens in vivo because I've seen behavior that makes me worry. I have a kind of an open mind about what the actual absorption spectra of blood is in vivo. I mean, I don't think I think it should be and usually is the same as what you could measure in a cuvette, obviously changing the optical, you know, oxygen saturation. But I've always had this nagging concern because sometimes I will make a spectral measurement and there's just evidence of something a little weird for the hemoglobin absorption, and it's bothersome. So I think it's all an open question still. Okay.
Perfect. The next one we have is from Evelyn. She asks, is some percentage of the signal lost in transmission in the optical fiber? Can it depend on the length of the optical fiber? And how long can the simulation of a photon interaction with tissue last?
Well, if what you're talking about are fiber losses, there is fiber loss. If a fiber bends, you're going to lose light. So yes, there are those type of things, and that becomes part of your instrument function that you have to correct for. So if you're delivering light with one fiber and collecting with another fiber, and those two fibers are in some fiber bundle, then if you set up your system and now the fibers bundle remains motionless, and you bring a standard to that fiber, and then you bring your arm or a tissue to that fiber, your calibration will cancel out all the effects of the fiber. If, however, you take a fiber bundle and you reach over to a standard and make a measurement, and then you reach over to a tissue and make a measurement, and the fiber is bending as you move it around, there is the potential for the fiber loss to vary because you'll get different bending within the fiber as you move the fiber bundle around, and you can end up having problems. And I've seen that in my own work. Giles and I found that when we played around with fiber bundles. It is always something to consider.
Cool. Last couple of questions now. Next one is from Lupe. He asks, instead of diffusion theory, what model do you suggest for air tissue interfaces with strong absorption?
Oh, well, then Monte Carlo. For two reasons. One, because you have an interface, and two, because you have strong absorption. Two good reasons for not using diffusion theory. Let me illustrate a boundary condition situation for you. If you simply use diffusion theory and consider an air tissue interface and try and calculate what the internal reflectance is, and hence 1 minus that is what is the escaping flux, you'll end up with a relationship between the escaping reflectance and the fluence within the tissue. So the escaping reflectance density is a fraction of what was delivered per centimeter squared. And the fluence just within the tissue is going to be so many watts per centimeter squared per watt that have been delivered. And so you end up with a ratio of 6 to 1. 6 times the reflectance, plus 1 actually, gives you the fluence within the tissue. When I ran that, when I did a Monte Carlo simulation and calculated, it's 7.1 times the reflectance plus 1. 1 because you're delivering 1 unit of light, but the diffuse light coming back gives you 7 times the escaping flux, or 7.1. Now, why? Because in Monte Carlo, you actually properly consider total internal reflectance of very oblique light, which remains oblique. So you end up having the opportunity for multiple scattering of oblique photons. And you end up with a little bit different answer than if you just consider this diffuse light 2 flux problem. So you get about a, 6 versus 7, so 1/6. So you're sort of in the 18% or 15% error in that relationship between escaping flux and fluence just below the surface when you use Monte Carlo versus diffusion theory. So that's an example of the type of difference near a boundary condition between Monte Carlo and diffusion theory.
Perfect. The next question we have there is from Anant, and he asks, for reflective spectroscopy, would MCML XYZ provide added benefit over MCML? What are your views?
So I didn't catch the first part of that.
Sorry, it says for reflectance spectroscopy, would MCML XYZ?
All right, so MCML and MCXYZ use exactly the same math. It's doing exactly the same thing. I mean, it's the same program. It's just that MCML has an RZ dependence. It assumes cylindrical symmetry. So you give a point source in, you get this cylindrical symmetric pattern of light distribution and escape. But the ultimate kernel that's doing the calculation is exactly the same as MCXYZ, where we just bother to have a Cartesian cube of X, Y, and Z to do our bookkeeping. But the propagation of the photon is identical. So there's really no advantage or disadvantage to one versus the other. However, if you can have cylindrical symmetry, the advantage is that when you're looking at your answer, you're actually integrating all of the escaping flux at a given radial distance. And so you get to average a lot of results to get the one answer for how it reflects as a function of distance. With XYZ, you're getting an answer for every XY position. And therefore, you don't get, your signal to noise is worse with MCXYZ because you're actually having to get an answer for every XY position of escape. Whereas with MCML, because you're integrating around at a given R, the ring of escape or at a given R, your signal to noise is much better. So if I had a simple problem of a point spread function, I would use MCML because I just get a result with cleaner results I can run for a shorter time. But if I had a problem where I was going to actually have variation in X and Y because I have some object down below, or I have two sources and I wanted to see how they interacted, then I would use MCXYZ.
Perfect. The next one we have then is how to solve the problem of light penetration into bone tissues.
Into bone tissues. Okay. Well, you just have to go to the literature and see what limited data there is on propagation of light in bone. If there's any type of oriented structure involved, I'm not sure there is, though. You'd have to consider that. But otherwise, what you have is perhaps a two-layer model. You have a superficial layer bone, and then you have a marrow area. Or you might have a three-dimensional structure if there's a very thin superficial layer that's a little bit different than the full thickness part of that bony part. In experiments that my students have done, they simply did R of R measurements, source detector fibers at different distances, and using multi-layer Monte Carlo answered the question of what optical properties were. But that was one study. And when I tried to review properties of bone, I recall it being a very limited amount in the literature. So it's an opportunity to do a lot more work.
If I can jump in there, Steve, just to give you a break, if nothing else, the question might also have been about how to improve light penetration into bone. And I believe Valery Tuchin and related groups have done some work in soaking skulls, for example, for 24 hours or longer in optical clearing agents. And apparently that does make very substantial differences to the penetration of light. Of course, that's not easy to do on live subjects, right? So we're probably talking about cadavers or animal subjects and so on. But the immersion in optical clearing agents for very long periods of time does seem to make a difference.
I agree. It can make a difference. I did work when I visited Tushin in Saratov. We did experiments on index matching solutions on live rats and in skin. And we had to soak for quite a while, and then we got differences in light penetration that were, maybe a factor of 2 at the most. But the inflammation that we caused, the intense irritation that was caused, made it essentially clear that in vivo work with such solutions was not really workable. So the only place where I've seen index matching really to be good is when they've got these clarity solutions and they're working with little embryos or little tissue biopsies where there might be a tumor, really small scale. They could let it sit for a couple days and then they get a clearing, and then they can do fluorescence tomography. Even in that case, there's always a little bit of residual scattering that the clarity cannot get rid of. Little localizations of where the fibers maybe are so cross-linked that they don't get clarified. So yeah, this type of index matching story is difficult, but that's where it's found the best application.
Okay, Aaron?
Yeah, last 2 questions now. This one comes from Hampus again. He asks, scaling down the spectral resolution of an instrument. Sorry there, I'll publish it so everyone can see it as well. Scaling down the spectral resolution of an instrument, e.g. due to cost reduction, and he just says, see my poster in the course, to around 10 spectral bands when looking at a tissue. What wavelength bands would you choose for such an instrument to be able to extract the most interesting information? And what kind of information is reasonable to expect to be able to find?
Oh, okay. Well, so depends upon the type of measurement you're making. Let's start with the concept of a camera or a total diffuse reflectance measurement. And so you're delivering white light everywhere, and then you're coming back, or you're delivering 7 bands or 10 bands of light and coming back and making images of each of those bands, or a single total reflectance measurement from each of those bands. What's interesting, you see, is that total reflectance is related to the ratio of reduced scattering to absorption. And if you have an error in your deduced value of mu sub s prime in the numerator, and you have the same error in the denominator, an error in the absorption, the ratio cancels the error and you get the correct answer for reflectance. So the trouble with those reflectance measurements are that that you can get the wrong answer in both scattering and absorption and match your data perfectly. Therefore, I've suggested that as long as you include a long wavelength measurement around in the 900s, preferably around 960, where water absorption is strong, and you assume a water content for the tissue, which you can be within 10%, pretty good estimate. Then that long wavelength measurement, when you try and match your theory to the measurement, you've only got water and scattering essentially. So the assumed water content dictates what the true scattering is. And once you have a good number for the scattering, you now have the wavelength dependence of scattering. So the scattering for all wavelengths is now specified. And now the absorption in all of the other wavelengths can be properly done because again, it's the ratio of scattering to absorption. So therefore, if you know the scattering, then you can deduce the proper absorption everywhere. Now that works, and that's needed to do. So my answer would be, you'd want to make measurements from, like in 400 or 450 on up through the 500 to 600 and the 700 and 750 range, and then make sure you have that 900 plus measurement. If you're doing R of R type measurements, 2 fiber measurements separated differently, it's different math. And now you can actually fit for the answer without having to assume water. So the answer to your question is that distributing your wavelengths through the visible into this up to around the 800 or 750, but then it definitely include a 960 or in the 900s where water is dominant. That would be my answer.
Perfect. And the very last question we have then is just a reply. It's a question you answered earlier from Valerie Grasso. She was saying that she's using your MCXYZ code to simulate 3D tissue domain, and that it was failing at some points on her. And she just replied to your answer saying, yes, the program crashes when the light source is on top of the water, and it works when the light source is at the interface / tissue.
Well, I would have to look at the details of the version of Monte Carlo she's using. There is I'd have to see what version she was using. In some of the versions, I have a Z surface specified such that you can deliver light from the top. I mean, you can always say where the light source is. So you can set Z source, ZS, to wherever you want it to be, and that's where the light will be launched from. And then if you set Z surface to some layer, then whenever light crosses that plane, it maps the XY flux coming across at that plane. But that wasn't in the earliest versions of MCXYZ, so I don't know if she's got the one that includes that. One possibility on the launching is possibly you don't specify the launch. You don't say ZS equals 0. You say ZS equals delta. Just within the front surface. I don't think that's the case, but that could be something she could try. So I'm a little confused by what she's bringing up, but I encourage her to send me an email, and I will, sort it out with her.
Okay. Perfect. That's all our questions.
That's fantastic. I don't know how many questions you're used to fielding at these kind of events, Steve, but that certainly seems like quite a lot. So there's obviously been a lot of interest, unsurprisingly, in what you've delivered. You've been at the head of this field for several decades now, and many of the professors that we will hear from or have heard from in summer schools on biophotonics and imaging have had your leadership in one way or another, or have interacted with you in one way or another. So you're really a great leader of this field. So thank you so much for your patience and for the kind way that you've given your time to both deliver the lectures and patiently answer the questions. It's really impressive to see your dedication holds up year on year on this. So well, thank you so much.
If I can comment, I found that most of the questions dealt with fundamentals about tissue optical properties, and even the Monte Carlo were essentially somewhat fundamental questions about properties and the interfaces. And there were very few questions about measuring optical properties, a little bit, but some, and no questions about laser tissue interactions and how you use the optical properties for dosimetry or for learning about tissues. Therefore, I think it was very good to start this session with, the school with this session, because it reinforces our shared concept that having some initial statement about the basics of optical properties and light transport really sets up the rest of the school, because all the other lectures are going to get into other topic areas. But if you start with a kind of a clear statement of what are tissue optical properties, how do they influence light transport, how do you measure optical properties, that really sets the stage. So that's my comment.
Yeah, I would echo that, and I would even say that, many of the early PhD students will say, well, why do we need to know this stuff? We just want to jump in and measure things. And in their third and fourth and fifth year of PhD, they realize that unless they understand the optical properties and the interactions, then it's very difficult to move their project forward and to develop some new knowledge in that area. So I think a lot of the questions, the really good questions we've seen, have been from people who've obviously been working a few years in the field and are getting around now to completing their PhDs and really need to know the answers to these questions. Yeah,
I tried to emphasize the difference between observation and optical properties, and with some examples like the color of coffee and adding water to coffee. That was one of my examples. Or why gingiva are pink and not orange. Some of these examples where observation can really fool you. But if you start thinking in terms of optical properties and geometry and architecture, then you can make sense of it.
Right. Yeah, and you've done a great job of that. So it's been a long session, a wonderful session. Very big thank you to Steve for your effort here and your offer to help. And there's no opportunity for the traditional applause. I will applaud you, but you can see the appreciation from the number of questions, and even people are already leaving their compliments. So thank you so much, Steve, for getting up early and getting stuck into this. So thank you so much. Okay, bye-bye, everybody. That's it from this session. We are back at 6 p.m. UK Irish time for Laura Waller's session. So she's in California. That will be still early days for her, but
is that in 20 minutes?
Yes, in 20 minutes. Yeah.
Okay.
All right.
Good.
Thank you very much. Thank you, Steve. Bye-bye now.
Thanks. Bye.
Bye all.